Using the vapor pressure curves in figure 11.2.5, estimate the boiling point of ethanol at an external pressure of 200 torr. B, estimate the external pressure at which ethanol will boil at 60 degrees Celsius. C, estimate the boiling point of diethyl ether at 400 torr. And D, estimate the external pressure at which diethyl ether will boil at 40 degrees Celsius. So figure 2.5 is plots vapor pressure versus temperature. As you increase the temperature, you increase the vapor pressure of the liquid. So anywhere along these curved lines represents the vapor pressure. So the first one they want us to do is at 200 torr for ethanol. So 200 torr, I hit the line at ethanol at about, I don't know, what do you think that is? About 45 degrees Celsius. Yeah, that's what I think. So at about 45 degrees Celsius, this is what the vapor pressure of ethanol is, 200 torr. B, estimate the external pressure which ethanol will boil at 60 degrees Celsius. So at 60 degrees Celsius, we hit the line at about, I don't know, 350 torr. All right, so at 60 degrees Celsius, you're going to boil at a pressure of 300 torr. C, estimate the boiling point of diethyl ether at 400 torr. So we draw a straight line across from 400 torr, and we see we hit the line at diethyl ether. So we hit that before 20, so I'd say that's about 18. All right, so you're going to boil at 18 degrees Celsius at a pressure of 400 torr. And estimate the external pressure which diethyl ether will boil at 40 degrees Celsius. So 40 degrees Celsius, I hit the line of diethyl ether way up there at 1,000 torr. So at this pressure, at this temperature, yeah, diethyl ether is going to boil. So that's what you get. Anywhere where you touch this line, this represents the vapor pressure, and it represents boiling at those pressures. Notice how they have the dotted line, right, normal, at 760 torr, right? So this would be the boiling point as we know it, right? So diethyl ether boils at 34.6 degrees Celsius. Ethyl alcohol boils at 78.3 degrees Celsius, and water, of course, boils at 100 degrees Celsius. Right, high boiling point due to strong hydrogen bonding between the molecules. Referring to figure 11.29, describe the phase changes and the temperatures at which they occur when CO2 is heated from negative 80 degrees Celsius to negative 20 degrees Celsius at a constant pressure of 3 atmospheres. All right, so that looks at about 3 atmospheres, and that looks like we're at about negative 80 degrees Celsius. So as I heat it from negative 80 to 20, I cross the line between being a solid and a gas. This is called sublimation. So when you go from a solid to a gas, skip the liquid phase here, we're crossing the line here. So CO2 sublimes at this particular pressure at about negative 80 degrees Celsius. So that's the way you read this thing. All right, B at a constant pressure of 6 atmospheres. All right, so we're starting at about here. All right, so when I increase the temperature from negative 80 to 20, I'm crossing both lines. I'm crossing the line between being a solid and a liquid. All right, so I'm melting here at about negative 60 degrees Celsius. And I'm crossing the line, I guess, at about negative 50 degrees Celsius, and this is where I'm boiling. So a temperature increase from negative 80 degrees Celsius to negative 20 degrees Celsius. I'm going through 2 phase changes. The phase diagram for neon is blah. Use the phase diagrams to answer the following questions. A, what is the approximate value of normal melting point? All right, so normal's at 1 atmosphere. So I hit the line at about 24 Kelvin. All right, so this would be normal melting point, 1 atmosphere pressure for neon. That's low. B, over what pressure range will neon sublime? All right, so it looks like the triple point starts at about zero 0.5 atmospheres and goes down to 10 to the negative 3 atmospheres. All right, so that looks like your sublimation range. And at room temperature, 25 degrees Celsius, can neon liquefy by compressing it? Well, the triple point, I don't know, looks like it's, all right, so if that's 30, it looks like it's before 25. So, 25, looks like we're right on the cusp. So no, we're not going to cross the liquid zone here. The liquid zone is going to be the temperatures from 45 to just at 25. So no, this doesn't look like I'm going to be able to sublime, meaning if I pressurize it, I'm not going to be able to cross the line and be where I'm going to cross the line at liquid. So no, we can't liquefy. We can only liquefy at temperatures below 45K and above 25K. So no liquefaction. All right, so covalent bonding. All right, so we're going into a new chapter here, right? Chapter 12, right? We're dealing with solids. Covalent bonding occurs in both molecular and covalent network solids. Why do these kinds of solid differ so greatly in terms of hardness and melting points? All right, the difference is with a covalent crystal, you've got atoms at the lattice points, and they're covalently bonded together. I mean, this is what holds the crystal together. So to break a covalent bond costs a lot of energy. So if you're going to melt something like diamond, you got to get it up almost like 5,000 degrees Celsius if you're going to disrupt these covalent bonds that hold it together. Whereas with something like sugar, where instead of having atoms at the lattice points, you got molecules at the lattice points, this crystal is held together by hydrogen bonds, all right, which are way easier to break. All right, so you've got molecules at the lattice points with molecular crystals, and you've got atoms at the lattice points with covalent crystals. One is held together by covalent bonds, and molecular crystals are held together by some sort of van der Waals attraction, right? Dipole-dipole, hydrogen bond, or induced dipole attractions. Oh, there they are. What kind of attractive forces exist between particles in A, molecular crystals? So as we said before, right, some sort of van der Waals force. So if I'm talking about solid carbon dioxide, it'd be held together by dispersion forces. Covalent network crystals, covalent bonds. So silicon dioxide, sand. You've got silicons and oxygens covalently bonded in the crystal. C, ionic crystals would be held together by ion-ion attractions. And metallic crystals would be held together by metallic bonds, right? This ultimate delocalization of electrons over the entire crystal. So we have core electrons and nuclei at the lattice points, and holding this together are the valence electrons, delocalized over the entire crystal. 11, indicate the type of crystal, molecular, metallic, ionic, or covalent network. Each of the following would form upon solidification. So if we've got solid calcium carbonate, that's an ionic crystal. Solid platinum would be a metallic crystal. Zinc oxide would be a ionic crystal. Table sugar would be a molecular crystal held together by hydrogen bonds. Benzene would be a molecular crystal held together by induced dipole forces or dispersion forces. And iodine is also a nonpolar molecule held together by dispersion forces. Which of the following substances would you expect to possess metallic properties? Well, metals, right, and alloys of metals, right? So a mixture of nickel and cobalt would be a metal, would have metallic properties. Tungsten's a metal, and so is germanium. Titanium tetrachloride or titanium 4 chloride is an ionocrystal, and scandium nitride is an ionocrystal. Classify the following statements as true or false. Substitutional alloys tend to be more ductile than interstitial alloys. All right, so before we tackle this one, we have to get an understanding of what these alloys are, right? So if I have copper metal, iron metal, if I take copper atoms out of this crystal and substitute in zincs, this would be an example of a substitutional alloy, something like brass. Where I need atoms about the same size in order to achieve this, right? And I substitute, literally, some of the atoms out of the crystal for other metal atoms. Whereas with an interstitial alloy, something like steel, we're putting smaller atoms in the gaps between the iron, and this is a way of stiffening iron up so that it won't bend. So this is what the steel is. It's mixing in carbon so that it's in between the gaps in the irons, and that is an interstitial alloy, right? In the interstices between the two, between the atoms in the crystal. So substitutional alloys tend to be more ductile? No. Oh, I'm sorry. Substitutional alloys, yes. Interstitial alloys are stiffer, right? That's the purpose of putting smaller atoms in the gaps in between the metal atoms. They don't slide past each other when you bend it. Interstitial alloys tend to form between elements with similar ionic radius. That's false. No, you need much smaller atoms to fit in the gaps between the irons. Non-metallic elements are never found in alloys. Well, no, that's not true, right? So, like with steel, we've got carbon in the gaps between the irons. All right, both covalent network solids and ionic solids can have melting points well in excess of room temperature. And both can be poor conductors of electricity in their pure form. However, in other ways, their properties are quite different. All right, so the only one we were interested in here was which type of solid is more likely to dissolve in water. And the answer is the ionic solid, because the energy required to break covalent bonds is so huge, and you're not getting a big benefit in terms of the attraction between water and the atoms that are being pulled out of the solid. Whereas with ionic compounds, you're getting ion dipole attractions. So just looking at the solution process, right? A solute has to be pulled apart. The solvent has to make room for the solute to get in there. So there's heat exchanges here. There's heat inputs and heat releases. So here's my rendition of water. All right, waters are attracted to each other by hydrogen bonding, and it makes kind of a hydrogen bonding web. Well, that has to be broken if you're going to let the solid potassium hydroxide in. Now, as we know from our solubility rules, this is soluble. So chances are it's an exothermic process if it's going to happen. Nonetheless, if I am going to put this crystal into water, I've got to put energy in to pull that crystal apart. I mean, these are strong ion-ion attractions. You know, the way it's amazing it comes apart at all. I mean, the melting point of this thing's really high, so big energy input if I want to pull this crystal apart so that it can be surrounded by water molecules. So now the anion, the cations are separated. So endothermic process to expand the solute, expand the ionic compound. I got to make room for this ionic compound to be surrounded by water, so I've got to expand the solvent. Again, breaking these hydrogen bonding interactions is going to cost you energy. So put in energy to expand the solute, put in energy to expand the solvent. Now, the solvent can surround the solute, and this will be a releasing process, right? We're going to get an ion dipole attraction between the waters and the cation and the anion. The negative side of water will surround the cations, the positive side of water will surround the anions, and we'll get ion dipole attractions. So the cumulative effect of all these ion dipole attractions is exothermic enough to drive this reaction, this process forward. It's not really a reaction, right? It's still sodium hydroxide. It's just separated, surrounded by waters. So expanding the solute costs you energy. Expanding the solute costs you energy. The release comes when the solute surrounds the solvent.